Hi guys, I'm back with another arcade PCB repair, and today on the bench I've got a Centipede PCB, which Centipede being a classic arcade game made by Atari in 1981. And this PCB came out of my dedicated Centipede cabinet that I have in the basement. I may be doing a video about that at some point. And the way that the board failed actually yesterday is that it developed some graphical problems. I can show you what I'm talking about on my test screen here. You can see that the game is actually running. You can see the play field, you can see the text, you can see the mushrooms. You can also see, if you look closely, that the game is running, or the demo mode of the game is running, because the mushrooms are disappearing here and there, because the player object is firing at the mushrooms, but you don't see the player object, and you don't see the shots being fired, and also you don't see the centipede or the spider that's usually hopping around here. So we have a complete loss of the motion objects, and in this video today I'm going to show you how we troubleshoot this problem, and as always I'm proceeding step by step, trying to explain everything so that you get some inspiration for your own arcade PCB repairs. Okay, so now where do we start? Where do we go from here? Well, in this case, this is a very good example where you can actually apply a very basic rule of arcade PCB repair, and that rule will probably have already been coming to your mind intuitively if you have done several arcade PCB repairs. But the rule that I'm talking about is that if you have a complete loss of a certain function or aspect of the game PCB, opposed to something glitching up, if you have a complete loss of a function, then that most probably means that the problem lies either at the very end of the circuitry that is related to that function, or that it lies at the very beginning of the circuitry that is related to that function. And it is rather unlikely that the problem is situated somewhere in between. And well, yeah, that's a very basic rule, and I will try to make an example to explain what I'm talking about. Okay, to explain it, I made up this little scheme here. Well, let's assume you have a PCB that has sound problems, and the sound problems are that you have a complete loss of all sounds of the game. Well, applying the rule that I just mentioned, that would mean that you would actually have to look at the very end of the circuit, of the sound circuit, to look for the problem, or you would have to look at the very beginning of the circuit, because you have a complete loss of a function. And with a sound circuit it's pretty easy to explain. Well, at the end of the sound circuitry you will probably find something like an amplifier. And the amplifier is the component that takes all the sound data and amplifies it so it can be output on a speaker. And everything that is being calculated in the sound circuit is in the end being led to the amplifier to be output. So if the amplifier fails, the sound circuitry will actually be still working, but you won't hear anything from the speakers, of course. So that is what I'm talking about. You have a complete loss of a function because of a problem occurring at the very end where everything merges together. So that is one possibility, but that's not the only one, because the problem can also be at the very beginning. And at the very beginning of the sound circuit would be something like the sound CPU and the sound CPU's RAMs, or the sound CPU's ROMs, and also the little chips, 74 LSs that are in between them, the glue, so to speak. That would be the beginning of the sound circuit. And if you have a failure of the sound CPU because maybe there's no frequency coming from the crystal, for instance, that will lead to a complete shutdown of the whole sound circuit, and you will also hear no sound for a different reason, of course, but the final symptom is the same. So also a failing of the circuit at the very beginning can cause a complete loss of function. Opposed to that, if you have a problem somewhere mid-circuit, you probably will not lose the complete function of the circuit, because from some point where it starts, basically in this case the CPU, the circuit often runs parallel in certain instances before merging again, for instance, to the amplifier. So if we are looking at sound, we might have an FM circuit where the music is generated, and we might have several digital sound circuits. So if a component is failing in one of those circuits, you will probably get maybe, for instance, only problems with digital channel 1, where maybe the sounds are sounding funny, or you have digital sound effects that are okay, but you have problems with the FM music, which is sounding funky in some way. And also, if a component fails somewhere here, and the basic circuit is running, you will much rather get some kind of glitching of the sound or the graphics or whatever function you're looking at, because the circuit is still running, the amplifier is still accepting signals. It might be getting some junk in because of a failed component in the middle somewhere, but it still gets some information, and the circuit is basically running. So what you will see here is rather some sort of glitching that will occur. Okay, so how do we apply those considerations now to the problem that we are having with this game? Well, we will have to look at the end of the motion object circuitry, and maybe also at the beginning of the motion object circuitry, and we will probably find our culprit around there. What is the end of the motion object circuitry? Well, if you watched some of my Double Dragon videos, you might already know what could be the end of the motion object circuitry, because it is very similar with many arcade games. Many arcade games generate their graphics in several layers, and those layers are generated parallelly. So the playfield is generated in some circuit that has nothing to do with a different circuit which generates the motion objects. And in the end, the game decides which layer it will actually display on the screen for a certain pixel, and it will actually select one of the layers for a screen position, and this is usually done with a multiplexer chip, like in this case also in the schematics for the Centipede PCB, we can see that there's a multiplexer down here that's getting some signals in, and I already looked into the motion object schematics, and I could clearly see that the output video signal from the motion objects are called GRY0 and GRY1, so those two guys are actually the output data that is generated from the motion object circuitry. So the loss of all of the motion objects could actually be explained by, for instance, this multiplexer completely ignoring the GRY0 and GRY1 signals. So we could, if we want to look at the end of the motion object circuitry, we could actually look at this IC right here and check the inputs GRY0 and GRY1, and we could see what they are doing, and if they are fine, we could check if the multiplexer is working correctly. Okay, and just to show you, there's a bit of motion object circuitry. The details are not really important, but important is that the output that is generated from this circuit is, well, those two signals right here. Okay, so again, it is the multiplexer is at position E8. It's an LS153, and we're going to look at signal lines 3 and 13 with our logic probe. Okay, so E8 is right here, E is there, and we got the 8 up here. So let's check pins 3, which is this one. Okay, this one appears to be low all the time. And 13 would be 16, 15, 14, 13. Okay, this is also low all the time, so there's actually no playfield data coming from the multiplexer. So I think we will have to go one step back and check in the motion object circuitry where the GRY0 and GRY1 signals are coming from. So we're going to look at the last chips that are outputting this signal as the next step. Okay, the signals are coming from E9, the chip next to it, which is an LS74, that is a flip-flop. The input signal is called MR0, signals are called MR0 and MR1. The output signals GRY0 and GRY1 are fed via the negative outputs of the flip-flop. So the next step would be to look at MR0 and MR1 and see if they actually carry some toggling data. Okay, so E9 is here, and we have pins 2, okay, pin 2 is toggling, so there's some data coming in, and 12 would be 14, 13, 12 is also toggling. So okay, so the playfield, the motion object circuit seems to be running up to this point. So let's see if this flip-flop gets some valid clock signals, and that there's no problem with the set or reset signals. If those signals were okay, then there would probably be a problem with this flip-flop. So, but let's check. Okay, so clock would be 3 and 3 and 11. Let's take a look. 9. So pin 3, clock is working. 11, 14, 13, 11. Clock is working. So that's not a problem. Let's look at the clear signals. 1 and 13. Okay, so clear is high all the time. This other one as well, so it is never being cleared. That is good. And what else do we have? We have another signal, a set signal coming in on 4 and pins 4 and 10. So this is oscillating on 4 and also on 10. So this signal isn't likely to be screwed up also. Well, so I guess it is very likely that the flip-flop chip isn't working right. So we could actually prove this if we attached a logic analyzer, but all the inputs seem to contain signals that are making perfect sense. So I guess it would be feasible to actually just replace the IC and see if this fixes the problem. So I'll start looking for a replacement IC, and I will unsolder this chip and put a socket in, and then we'll see if this fixes our issue. Okay, so I replaced the IC, but the bad news is it didn't change much regarding the graphical issue, and also when I take this thing out of the circuit and put it into my IC tester that I have here, it actually tells me 74 found. So this IC, this replacement chip, works well. So that actually was not the problem, even though if it looked like this flip-flop would cause the issue, because it would not generate a usable output signal. This does not seem to be the case. Okay, so even though this flip-flop is getting a wiggling input signal, it's on all its lines, and it's still outputting low signal all the time, it still appears to be working. That is actually possible because it is all really a matter of how the signals are falling together. So again, to prove that a complex logic IC like a flip-flop isn't working correctly, you have to look at it with a logic analyzer, and hooking that up sometimes takes a longer time than just replacing the part. But we don't actually seem to have a problem at the end of the circuit. As we can see now, we got signals everywhere, and the fact that there's no output, graphical output on the lines, does not seem to be the fault of the components that are working on the signals at the end of the circuitry. So we are coming back to our basic rule, and we are trying to look further into the beginning of the motion object circuitry. Okay, and here's what the beginning of the motion object circuitry looks like. It's actually a very common architecture. We have all the, this is the vertical position signals, and they are going into two multiplexers right here, and as alternatively selectable input signals, we have a connection to the playfield data signals, which are coming from the CPU. The CPU needs to be able to access the playfield, and not only it should not only be accessible via the positioning signals, which is required to display the playfield actually. So there needs, in the beginning, there need to be multiplexers, and these are fed into the outputs are fed into a buffer, and over here we have a logic gate, which is a 4-input NAND gate, as it looks. And I actually did already probe around with these components with my logic probe on the board at the location of these components, and I found something very interesting about this logic gate, which I'm going to show you. Okay, so again, what I did was I just was probing around these chips, and we actually do have the quad input NAND gate here, and it has inputs on pins 1, 2, 4 and 5. So those are all toggling, as you can see, but the interesting part is the output, which is pin 6, isn't really toggling, so this appears to be high all the time. For this signal to actually be switched to low, all of the 4 inputs would have to be high all at the same time, which might be an event that rarely occurs. But well, I looked at this probe for quite a while and it never happened. Also, I did reset the game a couple of times. This output stays high, and of course this is very suspicious of the gate, the logic gate, being stuck, because why would you implement a logic gate which outputs high signal all the time? You could leave it out of the circuit if it actually would only produce a high output all the time. I found another interesting clue when I looked at the signal with my oscilloscope, which I can show you. Okay, so I hooked the signal up to my scope, and you can see the result here. Let me just stop this signal for you. Okay, so this is the baseline, so this is 0 volts, and up here we have 5 volts, which would be a high signal, and it's high most of the time, as we saw with the logic probe, but there are some moments where the signal actually looks like it wants to do something and actually wants to turn to low, but as you can see here, when it is maybe wanting to turn low, it is still at a level of 2 volts, because you know, one line is a difference of 2 volts. So this, I don't think that 2 volts are really being interpreted as a low signal. So I think it should have been at least below 1 volt. So this is what our high all the time signal looks like. It actually is not high all the time, but somehow it is not really reaching the logic 0 level. So that leads us to the conclusion that maybe there's a fault with this gate, and the gate has a problem to actually put out a true low signal. And to actually verify if that is the cause of the graphical problem we are having, we could of course replace the gate. But in this case we could actually also, I think, try to add a resistor to this output signal, which is connected to ground, so that we can pull the output signal more towards the ground level, and then maybe get re-establish the difference between logic 1 and logic 0. So let's try if that works. Okay, so what did I do? I actually left the oscilloscope connected, but I attached a second black wire, which is going to a 1K resistor, and I attach this to the signal, and what we get on the scope now looks like this, and this looks much better in terms of where did it tick? Okay, in terms of a valid signal, because we actually now have a logic level which is low, and by attaching the resistor we actually pulled down the high level from 5 volts to 4 volts, but that shouldn't matter, and I can actually prove this because, ta-da, if you look at the screen you notice that the sprites are back, the motion objects. So okay, and if I now actually remove the resistor, boom, they are gone again. So, well, as a permanent fix, we could either connect the resistor between pin 6 of this IC and ground. We could solder it on the board, but I wouldn't really do that, because I think that this might be a dying IC that might get worse over time, and we might even lose all of our available ground level. So so it might actually be the case that if we fix the board this way, that the error would reoccur if this IC gets worse. So I would actually say let's go ahead and replace this guy, and we should be okay. Okay, so I got the IC out, and well, without the IC the game actually doesn't show any motion objects, and also it seems to be resetting, so this chip is actually probably used for something else as well. Okay, but I got this used chip from another game PCB that is beyond repair, and if I put that in, we have our motion objects back. Great. So the basic rule that I wanted to show you: if you have the complete loss of a function, always look at the beginning and the end of a circuit first, because that's those are the likely spots where the problem should be originating from. Actually turned out to be working for this example, which makes me quite happy. So the point of the video is actually safe. Well, and as always, thank you for watching my video. And if you liked it, you are free to subscribe to my channel and watch all the
other arcade step-by-step PCB repair videos that I did. Thank you very much, and until next time.